Okay, quick finishing up to last Tuesday's lecture. Is there an echo in here? You don't know. Maybe it's only from where I'm standing. Okay. Think it's going to make it hot? We'll have to see. Okay. Just a simple thing to tie off the last lecture. So, all right, we got a program. Okay, we used getchar last time. Getchar is part of the standard IO library. Its whole goal is to just get a character, one single character. You will note that its prototype there says it returns an integer. Okay? This is actually important. Now I'm also going to say it's stupid, but it is important. So if I say, because I want to get a char, if I say char c, here, while one do, I'll write my cat again. So c equals get char. If c equals EOF, then exit 0. Otherwise, put char c. Return 0, even though it's never going to get executed. Okay. cd temp. There we go. All right, I go ahead and compile this, and then I run it on itself. Works just fine. Okay. However, let's suppose I run it on the a.out. Okay, so ls-l a.out, 49,000 bytes. If I say a.out, pipe that to word count, right? So what does word count do? Lines, words, characters, okay? I only get 16,000 characters, okay? Or if let's say I say a.out into temp.text, and then if I do a long listing on that, we're going to see the same thing, 16,205. Any ideas what's going on? Let me change, I'll do it here. Let me change this to an int. Okay, now I get all 49. Okay. What's going on? I'm returning when I do EOF. EOF is pound defined to be -1. When I'm getting ASCII characters, right? ASCII characters are, the ASCII character set is limited from 0 to 127. Okay? And some of those are unprintable, so you don't get them. So the nice thing about the ASCII character set is I'm always, when I do a char, I'm always getting a char that's not equal to either -1 or 255. Now, EOF is pound defined to -1. If it's a char, -1 is also equal to 255 as an unsigned char. When I read it, and so if I have a byte in my file whose bits are all set, so as an unsigned char that's 255, as a signed char it's -1, getchar is going to read it, and if I'm storing it in a char, now C is going to equal EOF. If I store it as an int, it's going to be 255. It's not going to get typecast. It's going to actually, when these two get compared, the integer is not going to equal -1. It's going to equal 255. When I do it as a char, it's going to say, all right, these two chars equal. Even if one's unsigned and one's signed, it's going to convert them to the same. Okay, and then that's why it exits early. Okay? So if I then asked, if I take a hex dump tool, right? I taught you last time, I showed you XXD, which is going to be useful in your lab. Okay, I'm going to propose that if I use XXD to look at a.out, the first time I'm going to see FF, right, which is 255, is going to be here at that character in the file. Okay, so how do I do that? Let's do xxd-g1 temp.text grep ff. Yeah, that should work. Oh, nice. Maybe it's not going to work. Huh. Oh, that's because it's not there. All right, it stopped reading when it hit the FF. So what I need to do instead is let me run, instead of temp.text, let's do it on a.out. And now let's put the space in there. There we go. The very first one is right here. Okay. Now XXD gives us this in hex. Okay, so let's change it to decimal. I've got one that just does it because I do this enough. There it is, 208, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Do we say close enough? Close enough. Yeah, it's close enough. All right. So, you're never going to call get char. Maybe you are going to call to get char, but if you do, use an int. Now, it's dumb, in my opinion. It's dumb. It's kind of like using a sledgehammer, right? I'm using a 4-byte value just so I can differentiate 257 values, right? Because I can't do it in a char, but it's good for you to see and know. Okay, questions on that? All right. I thought I had links in here. Okay. Unfortunately, this part of the lecture, it's best for me to go over canned and not live because I've got pictures drawn on the canned stuff. Okay. So I am going to follow the lecture notes here, which means you're just going to have to eat lecture notes. But that's okay. Here, I'll make this so big it's going to be hard for you to read anything but what I want you to read. But I will put this here. Okay. And you can read the text or I can say it. I'll say it. When you create a file in Unix, you modify 3 places on disk. Okay? That's important to know. It's important to know what each one of these is. Okay? First, you got the bytes of the file itself. So here, when I'm saying this is f1.text, that's what's being stored in the file are these bytes, the ASCII character codes for these bytes in a new line at the end. There's also going to be something created called an inode, which is the metadata of the file. This contains information about the file. So its size, its protection, the modification times, all of those things, ownership, all of those things are stored inside the metadata, which in Unix is called an inode. Okay? The inode itself is stored on disk. It's also cached in the operating system memory so you can be fast, but it is stored on disk. It has a block number, bless you. Okay? And then finally, the name has to go someplace. So the name goes into a directory file. So the directories are actually just files. Okay? So you're going to modify the directory now, and what you're going to do is you're going to put a mapping or an association of this name and the inode number, the metadata, into the directory. And that's it. Okay? That's it. And this is how files and directories work. So that if I say open f1.text, what has to happen? Well, I need to first be able to access the directory. Once I access the directory, I'm going to find that mapping between the file name and the inode number. Then I'm going to go to the inode, and then I'm going to look, do I have permissions to open this file? Okay? If I do, okay, then the inode actually tells me where the file is on disk. Now, what I have here in this listing is LSLAI. So that's, what is that saying? The L says do a long listing. The A says list files that begin with dot, because it normally doesn't do that. And then I says list the inode number. So here are the inode numbers of all of these files, my directory, my parent directory, me, and the lecture notes. Okay? And so I have a picture of this. This is why I do the canned example. I have the picture of this here in the lecture notes on a beautiful LibreOffice JPEG, okay, where I'm showing the various various parts on disk that are stored for this file. So you got the file itself, and it's going to be taking up a disk block. It'll take up a whole disk block, which will be, depends on the machine. Half a K, a K, 4K, just depends. Okay, or if it's an SSD, it's sitting on an SSD. But it's taking up the whole block. You don't share blocks between files. And that's where these bytes are sitting there. Okay, is that wasteful? We don't care, storage is free. Okay. Then we have the inode. Okay, so the inode is sitting there, it has a number, and the operating system knows how to take this number and find the proper block on disk that contains the inode. In fact, it contains several inodes, right? Because inodes are smaller than a disk block, and the OS will pack those into a block. And then it's going to say, okay, here's the number, and here's a bunch of metadata about my file, right? So here's how big it is. Seems too big. Where are the links? This isn't the right file. Here's my file. I'll get to that one. Okay. Inode size is 15, that makes sense, right? Protection mode, and then the inode stores this. You won't be able to see it, but the inode will store where can I find the file. And if it's a big file, it'll contain a bunch of information about how to find the blocks, right? So that matches that. And then in my directory, now, directory will be stored in a specific format. I don't know what that format is, but that format will basically say, when I get to my file, here's my file, there's its inode. And so again, when I open, it's going to go from here to here to here to eventually here. Okay. And then you'll note, right, the directories are themselves just they're just name and inode binding. So current directory, that's where I have this inode here. Right, and its size is 38, which is small, and this will vary from machine to machine. Some machines, your directories are always a K at least, but some of them they'll be small. Well,
where are the inodes stored?
On disk, and the operating system knows where to get them. In fact, they're usually stored in a middle sector on your disk. This is back in the spinning media days because they want it to be fast to find your inodes. But they're also cached in the operating system. That's why things are fast. But they're stored on disk, and the operating system knows that if I say this inode, it knows where to find it. Yeah.
What exactly does on disk mean?
So you gotta. So, all right, let's go with the easier one. If I got an SSD, do we all know what an SSD is? Like a USB stick, but you can plug them into your backplane. All of these things are going to have controllers on them. Now I'm teaching operating systems and not this class. Okay. All of these things have a controller on them. And then your operating system will basically say, and they're going to have numbered blocks, and your operating system is going to say, get me block 257. And then it's going to issue that command on the memory bus, and then the operating system is going to go do something else. Okay? And then the device, whether it's an SSD or a disk drive, is going to fetch that block, however it fetches the block, throw it using DMA into a buffer that the operating system has given it in memory, send an interrupt to the operating system and say, hey, your block's ready. And then your operating system will go grab that block. But if it's an SSD, it's just, that's just solid state electronics. If it's a disk, it's going to be a magnetic platter that rotates like a record. Do you all know what a record is? Does that, and then it's got it is much like, it's got an arm with a little head on it, and it'll go back and forth, and then it'll go to the proper track and wait for it to spin. Operating systems. You'll get that from whoever teaches 361. And if you're lucky, you get to write it. That's the best part, is when you get to write these things. Oh, it's so much fun. It's so hard. Mars makes you write RISC-V. If you take his graduate operating system class, you will write RISC-V. He's ambitious. I'm not that ambitious. I would never do it. When I taught operating systems, you wrote an operating system on a simulated machine, because then it's easier. But it's fun. You know what's not fun about operating systems? Students who don't want to be there. That is the worst part about operating systems. And thank goodness 560 is no longer required for graduate students. It's why I stopped teaching it. It's because whiny ass students who didn't want to be there made me angry. Made me so angry I got mad at them one day, and the next day I bought them pizza because I just let them have it. Because they were going, I don't want to be here. Now maybe you all are like that too. I apologize. I recall this class still is required, isn't it, for 2 majors. I'm actually of the belief it should only be required for one. I think it should only be required for computer engineering and not for computer science. I think it's useful as hell for computer science, don't get me wrong. But I kind of think if you're going to end up going into front end or even if you're going to end up being like a machine learning engineer, you don't need this class. It's going to help you, but you don't need it. And I wouldn't get to see all your smiling faces. Okay. That is how it works. That's how these things work. Now, I will go here. Should I just remove everything? All right. Echo, here, echo, hi, into temp1.txt. Okay, so now we'll do the same thing, ls-lai. Okay, now I got a lot more files in here, right? But you'll note here I am, right? And basically in my long listing, this is all the stuff that's in the inode. This is all the metadata. So protection mode, number of links, okay, size, who owns it, what my group is, modification time, name. Okay. Now, if I can create a link. So link temp1.txt to temp2.txt. Okay. Now, what has that done? That is actually just in this picture, which I've deleted. No, it still exists. In this picture, what this does is create a new entry here in the directory. That's the only thing it does. It doesn't, well, it does touch the inode a little bit. It doesn't touch the bytes, but it changes this, or it adds to this, and it adds a new listing. It says f2.txt and the same number, right? There it is, same number, 803. Okay. Now it does change the metadata because the metadata includes the number of links. So it will change the inode and add the number of links, and that's why this field changed when I did the long listing. Okay, but it didn't touch. You'll note it didn't mess with the modification time. Everything else looks the same. Okay, so now I can treat these equally, right? If I type vi temp2.txt and I change this to hi there, and I can't spell. It's because I forgot lunch. It's actually a lie. That's not a lie that I forgot lunch. I did forget lunch, but I'm one of these people, I can go until 8 tonight without eating, and it's fine. I don't become cranky. Okay, you'll note, modification times, everything, these are identical. The reason is because these guys share the same inode. This is the same inode. The only thing I did was add a new name to inode binding. And so the bytes themselves have changed. If I say cat temp1.txt and cat temp2.txt, right, they're pointing to the same disk block. So that's why it looks like, hey, they both changed. They haven't both changed. One thing has changed, but they both point to it. Yes, Matt?
Is there ever a time that you would want to have two files going to the same item like this?
Yes.
Or would it just be like a waste?
No, this is a useful feature. I mean, I do it a bunch. It's frustrating. There are parts of it that are frustrating. It can be very useful because there are times where you would just like to have the same file, the exact same file, in two different places. Where does it suck? Git. Because Git doesn't retain your links. Unless Mr. Squires knows a way to make it do it. No, okay. Or any of you. I just say him because you read more manuals than other people do. So, okay. But yes, it's very useful. It's a very useful functionality to have. And so you can do it any number of times, right? So I could say ln temp2.txt and temp3.txt, and it didn't matter if I did it from temp1 or temp2 because it's the same inode, right? Now they're all sitting here like that. If I chmod one of them, so chmod 0600 temp3.txt, they all change. Why? It's the same inode. Okay. Yeah, Jason.
Like half of like the Unix system folders, like dev devices, they're all links to other places where they actually the real files are.
Right. Is that a symbolic link or a regular link?
In dev, I think it's regular.
It's a hard link. Okay. Yeah. Obviously, it's operating system. Whatever your operating system is going to support. But it's it is super useful. And even Windows has something like it. I guess everything's Linux under the hood now, right? I mean, even Windows is Linux under the hood. So they get it. Now, okay, so they're the same. And now there's no hierarchy. There's no like, hey, I created temp1.txt, so it's got priority. It's just a name to an inode, right? So if I get rid of temp1.txt, it's cool. The others are fine. I can still cat them, temp2.txt. We're all good. Temp3.txt, good. They're still there, right? You'll note that link field changed. right? And then when I finally do that, now the links field in the inode, which I maintain, turn to 0. When that happens, we delete the file. That's when now the bytes go away on disk. Okay? It's very simple, but when you don't see it, it's confusing, I think. But that's just what they are. Every directory has 2 files in it, dot and dot dot. I went through this before, right? Did we CD all the way to the root? And then CD to dot dot in the root? I don't remember. I think we did. Oh, I did it in the video. So maybe you didn't see it. Okay. There, I'm at the root directory. The root directory still has dot and dot dot. What is the parent of root? Root, circular. Okay. Now, these directories are themselves files. They have inodes, right? And so, let me create a directory. Well, there's one right there, circ. Okay? You see circ is sitting there at 547. Okay? If I do an ls-l AI of circ dot, we are going to see right there, 547, 547. You'll also note circ slash dot dot is going to equal my dot. These are hard links to each other, right? So the directories are all linked to each other. You don't get to create the actual links explicitly, but when you call make dir, you do. Right? You're actually creating a bunch of links to files. Okay? And that's why, for example, right, this directory, the parent of this directory, my temp directory, has 11. Because it has 11, it has a bunch of subdirectories. Okay? You can do a symbolic link. Let me full stop. There is something called a symbolic link, which is unfortunate in my opinion. It's kind of a hack, but it's been a hack that's existed forever. If I say ln-s temp2.text to temp3, oh, I've already deleted it. So here, echo hi into temp1.text. Okay, and now I say ln-s temp1.text to temp2.text. And now I do a ls-l-ai. You'll notice it's different. I now have this weird listing. First off, it says, hey, this is a symbolic link. So it's a special file. It is a file. It has its own inode, right? Has its own size, which is in fact equal to this. So it actually just stores the string name of the file that it's linked to. So now this one, there is a hierarchy. Here's my main file. Here's my kind of pointer to it, which is a symbolic link. But I can do anything I want. I can say chmod 0700 temp2.text, and then you're going to note that that didn't change this one. That changed this one. Right? If I vi it, temp2.text, and say hi there, right? And then I cat temp1.text, there it is. Right? It changed. Right? And the modification time on the link didn't change. The modification time on the file changed. Symbolic links are okay. I try to limit their use a lot because they just get in trouble when things go stale. The nice thing about a symbolic link is you can link to a directory. You can't do a hard link to a directory, but I can do a symbolic link to a directory. Also, if you type df, it'll show you all the different partitions of your drive and all the network drives that you're attached to. You can't make symbolic links across those or regular links across those file systems because they're on different disks. But you can make a symbolic link. Okay. Can I make a hard link from my file to your file? Yeah. Might not want to. What sucks is if I do that, then now you can't delete that file. Sorry. Now with the symbolic link, you can. So with the symbolic link, right? So now if I remove temp1.text, you're going to notice the symbolic link, nothing's happened to it. But now if I say cat temp2.text, now it's going to give me, it's going to give me that same opening error that you get when it doesn't exist.
Would those files have to be on
Not with a symbolic link. Well, as long as the file system has been set up so that you can read both files on the same computer. Like our lab machines, right? We're all running network file server. So each one of our home directories is on a different machine. Now, if your home directory is on a different machine than mine, we can't do hard links of our files to each other, but you can do symbolic links. Okay, and that's because when you make a symbolic link, I don't give a crap, right? The operating system is reading those bytes and then saying, okay, now I'm going to go to this file. Okay. Not that important, but good to know. Well, actually, no. What is important about this is that you get this whole three-part structure of a file, right? Bytes, metadata, directory entry. Those are three things, and that structure is something you should know exists because it's just important for you to know. Okay. I lied slightly. If you open a file and then while it's open in your program, in another program you delete it, you still have the file. Okay? The operating system won't delete it until you close that file descriptor. And now if it has no links and no open file descriptors, now it'll go trash the bytes. Right? So we can play a mental exercise called hide my porn. Right? You got your porn on your computer. You don't want your spouse to see the porn. Don't get me in trouble. This is just a joke, okay? This is just a joke, but it's a funny joke, so laugh and don't get offended, please. You don't want your significant other to find your porn, right? So what you do is you open a file, have a program open that file, and then you can delete your porn. But then your program has to be set so that when you hit a thing, then it goes ahead and reads everything and writes it to another file, right? So you got access to the bytes even though no one can get to them except for your process. And of course the operating system, and of course those programs that read your disk. All right. So anyway, it's a fun little thought exercise, isn't it? Okay. All right. I'm joking, okay? I'm joking. This is why I have to delete my videos, right? Maybe next year I can't say that. So, all right, let me just double check that I got everything I need here from these lecture notes. Yeah, we're all good. Okay, let's click.